Hello everyone, welcome to my talk. In this presentation, I'm going to talk about balance allocation in dynamic hypergraphs. This is a joint work with Catherine Greenhill and Bernard Matz. Let us first define our setting. Assume that we are given a set of n bins and n sequential balls, where our goal is to allocate balls into the bins so that the maximum load is minimized. And the maximum load is the maximum number of balls allocated to any bin after allocating all n balls. The balls into bins model are quite general, and they have been seen in many places, such as random graph process, hashing, de-randomizing hash function, and load balancing in distributed networks. For example, we may consider bins as servers and balls as sequential requests that should be satisfied by the servers. And our goal is to minimize the response time for any request. Here we see that the maximum load is directly related to the maximum waiting time for any request. A very simple and intuitive mechanism is called one-choice process, where each ball picks a random bin uniformly at random, and the ball is allocated to that bin. It is proof that using this mechanism, the maximum load is at most log n over log n plus some constant. Azar, Brother, Carlin, and Opfal introduced the balance allocation known as power of d choices, in which every ball chooses d bin uniformly at random, and then the ball look at their load information and goes to the one bin with minimum load. And if there is a tie is broken randomly. They show that after allocating n balls, the maximum load is log n plus some constant. Surprisingly, we see that when we increase the number of choices by at least one, the maximum load exponentially decreases to log from log n in one choice process. And that's why it is called the power of d choice. The original balance allocation idea is based on the fact that each ball picks d bins independently and uniformly. However, in many applications, choosing any random set of d bins is not possible, or it's very costly to be applied. For instance, consider a set of servers that are interconnected by a network, and assume that random request arrives at some region of this network. And in order to minimize the communication cost, it is important that request is satisfied by nearby servers. So it would be very applicable to consider these types of balance allocation where some underlying structure are assumed, and hence a dependency among the bins exists. Therefore, it might be possible to directly apply the original balance allocation in such a setting. Motivated by this application, several variations of balance allocation model has been studied. For instance, the balls into bins via local search, geometric generalization of power of d choices, graphical balance allocation. For instance, in the first result, which is called the balls into bins via local search, a ball appears at the underlying network, then the ball chooses a server or a bin uniformly at random, and then the ball is only allowed to search in a local area to find a bin with local minimum load and then allocate itself to that bin. One of the first results in this area is called balance allocation on graphs, introduced by Kentabadi and Panigrahi. Here, they assume that the bins or servers are interconnected as a graph, and then when the ball arrives, it picks a random edge from the graph, and then look at the bins incident to the endpoints of the edge, and then the ball is allocated to a bin with lesser load. Here, they show that provided the graph is regular and sufficiently dense, then after allocating all n bins, the maximum load is of order of log n plus some constant, which depends on the density of the graph. The second result, and in fact, the second main result in this area is known as balance allocation on hypergraphs. In this result, the author assumed that there is an underlying structure for the bins, which is in fact a uniform hypergraph. And when a ball arrives, it chooses a hyperedge uniformly at random from the hypergraph. And then the ball is allocated to a bin with minimum load among the bins within the hyperedge. He showed that the maximum load is a constant with high probability. However, the hypergraph should satisfy some mild condition, which is called the balancedness. To see an example of hypergraph satisfying the balancedness condition, let us look at the following hypergraph. Consider a set of servers or bins that are organized as an n cycle, and each hyperedge is a path of length s from this cycle. And the union of all these equal-sized paths builds a hypergraph. Now, when a ball arrives, the ball chooses a path of length s randomly, and then the ball is allocated to a bin with minimum load belonging to that path. One can see that in this hypergraph, there is a balancedness condition, which means that the probability that a bin probes by a ball is order of s over n, where s is the size of the hyperedge, or here the size of the length of the path. So here we can conclude that in this example, we have a hypergraph satisfying the balancedness condition, and applying the result from Godfrey, we can conclude that the maximum load is constant with high probability. So far, we observed that we have two main results about balls into a structured bin. The first one defined by Kentabadi and Panigrahi is called balance allocation on graphs, where they only consider the case that the number of choices is 2. And the second main model was defined by Godfrey, which is balance allocation on hypergraphs. As we see here, in two main results, the authors only consider two cases, where d is equal to 2 and d is at least log n. So in our result, which we call it balance allocation in dynamic hypergraphs, we are trying to close the gap between previous result and consider the case where the number of choices is between 2 and log n. Comparing with the original balance allocation, we are interested to see how we can get the effect of power of d choices in such a structured balls into bins model. In our setting, we consider a dynamic hypergraph as underlying structure for the beans, so that this underlying structure is a hypergraph which is exposed over time to the system. In fact, we define a dynamic hypergraph as a sequence of hypergraphs with the same ground set, but the edge set may change over time. We denote the hypergraph with notion of h1 to hn to hn. Here, the n denote the set of n beans or server, and E sub t means the set of hyper edges which change over time. Moreover, we here assume that all hypergraphs have the same set of nodes or vertex, which denoted by set of n. So we may apply the Godfrey model so that when a hypergraph exposed to the system at time t, a ball chooses a random edge from the hypergraph, and then it looks at all beans contained in that edge, and the ball is allocated to a bean with minimum load. And if there is any ties, they are broken randomly. However, we slightly change the Godfrey result so that each ball picks the random beans from that edge, and then the ball allocated to a minimum load among these T beans here. So let us review our model. So first, we need an underlying hypergraph, which is denoted by h1 to hn, arriving over time. And then we fix some d, which can be between 2 and log n. Then over a time, and we consider n time step. So assume that at time t, the t's ball arrives. Ball picks a random edge from the hypergraph ht, which is exposed to the system at time t. And then again, d beans from the random edge selected, and the ball is placed on the least loaded bean among these d beans. And if there is a tie, ties are broken randomly. Comparing with original balance allocating depends on the structure we define here. We may need much smaller source of the randomness, which this model also can be seen as to be studied for a way to de-randomize the balance allocation process. Now the main question is that under which condition we can get effect of power of D choices in our model. The first condition we need here is called the visibility. And what is the visibility number? Let us assume that we are given a dynamic hypergraph in n time steps from h1 to hn. And for every pair of beans, we consider to define the visibility number, which is the number of times a pair appears in some edge in this sequence of hypergraphs. And this sequence of hypergraphs of length n is called epsilon visible if for every pair of beans in this set of n beans, the visibility number of this pair is at most s times n to the 1 minus epsilon. And then this sequence of hypergraph is called epsilon visible. Beside this condition, also we need to have the condition which already defined by Godfrey. The first condition is balanceness, which says that for every bin I, if given the fact that our hypergraph is uniform, then for every bin, probability that the bin is chosen by the t-ball is bounded by beta times S over n, where beta is a constant. So here we see some kind of the uniformity for all bins, and the bins, when a ball arrives, there is no priority in the bins, and all have the same probability. The last condition is that for a given S uniform hypergraph, the S should be at least as high as log n. However, in our model, we can define S to be a function of D. For example, if D is a constant, we don't need to have a large S. For example, if D is a 5, for example, it's enough to have a S to be of size 10. However, to have a more accessible proof in the paper, we also add this result, this size condition. So if we are given a dynamic hypergraph and we consider the balance allocation on this dynamic hypergraph, and the dynamic hypergraph also satisfies these three conditions, then we have our main result, which says that the algorithm or the balance allocation on dynamic hypergraphs achieve the maximum load of at most log d log n, which is as good as original balance allocation defined by Azar and others. Additionally, we show that the condition 1 and 2 are necessary. Otherwise, for example, if we have a dynamic hypergraph which doesn't satisfy the second condition here, then we can show that the maximum load is much more than log n, and it would be of order of log n. Our proof is based on a witness tree technique, where we briefly sketch here. As we already said, at each time when a ball arrives, a hypergraph exposed to the system. And to analyze this model, we consider a random hypergraph which is simultaneously built during the balance allocation. We know that each ball picks D random bins, so that at the end of allocating all n balls, union of all these D choices make a D uniform hypergraph, where its ground set is a set of bins that may contain some balls. So for example, here, when we allocate all n balls, here we can see a random D uniform hypergraph, and where the ground set is some bins with balls. And what we observe is that with high probability, the random hypergraph does not contain any connected component of size log n, whose nodes have load at least some constant. Here, by connectivity, we can say a hypergraph is connected such that there is a sequence of between any two hyper edge. There is a sequence of hyper edge such that every two consecutive one are intersected. So we have a connected hypergraph, and we observe this key lemma about this random D uniform hypergraph. Then we use witness tree construction, which is a deterministic construction to build a witness graph. Here, assume that at the end of allocating n balls, we have a bean whose load is at least L. Then, because we have a bean, because we have a ball at this height, then we can conclude that there was a corresponding D choices here, such that the minimum load of these D choices is at least L minus 1. And then recursively, we start building a tree-like structure level by level. And then we end up with a tree structure of height L. And what we observe is that the size, this is a connected component of the random hypergraph of size at least D to the L. And now, because the deterministic construction guarantees that if we have a bean of load L, then there is a connected component of size DL, where every bean has, for example, has some load. So using the key lemma, we can conclude that the maximum load is at most like N. And we prove our main result. Let us summarize our result. So here we introduce the notion of epsilon visibility for dynamic hypergraph. And using this notion, we prove that if a given dynamic hypergraph satisfies this condition, then the algorithm has maximum load of at most like D like N. Moreover, we can show that these conditions are necessary, and also we can replace the hypergraph with dynamic graph and get the power of 2 choices. Thank you for your attention. If you have any question, please feel free to send me an email. Thank you.